Welcome to Varum LLC video overview on the Lean Architecture, a systems-level guide to manufacturing.
Any manufacturing process, left to its own devices, naturally tends toward entropy. Machines wear down and tolerances drift, causing high-speed assembly lines to accumulate variability until they eventually jam and lose capacity. This instability originates from three structural sources: muda, which is non-value-adding waste; mura, the unevenness in production flow; and moody, the physical overburdening of equipment and operators. Lean manufacturing and Six Sigma provide a closed-loop framework to counter this entropy through systematic interventions. Over 30 distinct tools operate within this system, each serving as an intervention at a different resolution, from high-level strategy down to statistical optimization. To see how these mechanisms interact, we will build this lean architecture layer by layer, starting from a blank factory floor. Approaching the factory as an interconnected ecosystem allows every tool to serve a specific structural purpose within the broader workflow. Optimization begins at the executive level. Without a clear definition of value and a strategic direction, physical changes on the floor lack a measurable objective. Hoshin, or policy deployment, aligns long-range corporate strategy with daily floor-level targets. This is achieved through catchball, a negotiation process across organizational levels that ensures every department executes the same tactical plan. These strategic targets are converted into specific forward-looking key performance indicators and SMART goals to drive measurable changes in operator behavior. With the strategy set, we move to the floor level. Before altering any workflows, we must accurately diagnose the current state of physical movement. A spaghetti diagram formally tracks these erratic paths. By tracing the continuous flow of operators and materials, we expose and eliminate excessive transportation waste. Value stream mapping elevates this diagnostic by churning both the material and information flows. This allows us to isolate system bottlenecks, such as inventory pileups that stall the entire production cycle. To classify the inefficiencies exposed by the map, we use the 8 forms of waste, categorized by the acronym downtime. This creates a standard vocabulary for identifying defects, overproduction, and waiting periods. These diagnostic tools do not fix the factory. They provide the exact coordinates required to deploy our tactical tools. We stabilize the physical workspace using 5S and the visual factory methodology. This involves standardizing tool locations with shadow boards and defining workflows with color-coded floor markings. Visual standards shorten the time between an event and an operator's response. When operational parameters are visible on the floor, an operator can identify an abnormality without searching through manuals. Next, we calculate the exact pace of customer demand using tapped time. This formula divides total planned production time by the customer demand over that same period. All sequential cycle times across the factory are then balanced and tuned to synchronize with this takt time heartbeat. We measure the efficiency of the machinery driving this flow through OEE, or overall equipment effectiveness. This metric tracks the availability of the machine, its production speed, and the quality of its output. By tracking the 6 big losses, such as breakdowns, minor stops, and scrap, we can identify specific performance drains and improve the overall OEE score. Integrating these tactical flow tools creates a predictable, continuous production sequence from previously isolated processes. We now shift our focus to workstation-level quality control, specifically addressing the costly impact of human assembly errors on the line. Poka-yoke is the specific mechanism of mistake-proofing. By embedding physical constraints or warning sensors into the fixtures, we can prevent errors and drive defect escape rates towards zero. For high-speed machinery, we must implement Jidoka. This gives equipment the ability to automatically detect abnormalities, such as tool wear or parts that fall outside of tolerance. When a defect is detected, Jidoka triggers an on-don system. This instantly stops the line and uses stack lights to alert supervisors, preventing the defect from propagating downstream. By anchoring quality within the process architecture, the system reduces its reliance on downstream inspection and catches failures at the source. When visual lean tools fail to resolve complex, invisible variants, the system must deploy the statistical rigor of Six Sigma via the DMAIC framework. We proactively score risks using failure mode and effects analysis. By multiplying the severity, occurrence, and detection of potential failures, we generate a prioritized risk priority number. Next, we perform measurement system analysis, or gauge R&R. If the gauges themselves are flawed, the baseline data is unreliable, and any subsequent process adjustments will be ineffective. To remove human assumption, we apply statistical hypothesis testing, evaluating p-values through ANOVA or t-tests. This validates whether a suspected root cause is actually responsible for the process variance. Regression analysis is then used to mathematically model the relationship between input variables and the output yield, allowing us to predict how the process will perform under different conditions. Design of experiments, or DOE, systematically tests multiple parameters simultaneously. This isolates complex interactions between variables to find the absolute optimal machine settings for maximum yield. Statistical process control locks in these settings. By monitoring data points within calculated upper and lower control limits, we can track process stability over time. Finally, capability analysis, or CPK, provides statistical proof that our stable process remains within the customer's tolerance limits. The Six Sigma engine replaces managerial guesswork with a high-confidence statistical model of process capability. Looking at the fully optimized factory, we must address a physical reality. Without sustainment mechanisms, the system will naturally regress towards its original entropy. Control plans prevent this regression. They formally document the monitoring methods, control limits, and reaction protocols required to standardize these improvements long-term. Common boards ensure compliance using highly visual red and green T-cards to standardize daily safety and 5S audits across the factory zones. Performance is tracked hourly through short-interval control, while black belt storyboards ensure that these successful improvements are replicated horizontally across other departments. Maintaining this architecture relies on the human element. Lean is driven by continuous scientific thinking, rooted in the plan, do, check, act cycle pioneered by W. Edwards Deming. Toyota Kata provides the daily coaching routine needed to build these scientific problem-solving habits in every employee. Kaizen events and quality circles empower frontline operators to solve localized problems, contributing to a broader culture of total quality management. The final evolution of this architecture is digital lean. The physical factory is mapped into a digital twin, pulsing with live data streams. Integrating IoT sensors and cloud-based analytics into lean protocols removes manual data collection bias and accelerates the speed at which the system responds to problems. Lean and Six Sigma integrate into a thermodynamic architecture, creating a self-correcting enterprise that maximizes customer value at every stage.
Are you now ready to eliminate operational waste and improve your EBITDA? Please book a free 30-minute discovery call. No commitment, no pitch. We identify your #1 bottleneck and outline a clear path. Visit our website or call us at 262-432-3118. We provide operational mastery on your schedule.